Hi everyone. Should we get started?
Yeah.
Yeah. Okay.
Yes.
So welcome everyone, and thank you for joining us. I'm delighted to introduce Dr. Gera Taubkin, who's principal consultant at WSP, and he brings expertise in sustainable urban mobility. And today he's going to walk us through some innovative and data-driven approaches to redesigning transit networks. Please, can I ask you all to keep your microphones on mute during the session, and there'll be time at the end for a question and answer session. So with that, I'll hand over to Dr. Gera Taubkin to lead us through today's session. Gera, the floor is yours.
Okay, thank you very much. So first of all, what I would should say, good morning, good Canadian morning, ladies and gentlemen, and of course, other day periods. Thank you for inviting me, giving me this incredible stage. And I am sorry, I can't speak Spanish, but excuse me, I don't speak English as well. So actually we can speak transitish a little bit. What I want to say more, I wouldn't want you to take my presentation as such a ultimate true. Opposite to this, I would welcome discussion, creative critique, from which the true may emerge. And towards introduction, I structured my presentation with two key considerations in mind. First, the time is too short to explore deeply even a single topic in transit planning, especially since there was also a scheduling mix-up regarding the duration of presentation. And second, what I understand, the audience here is quite diverse. What interests some may bore other. And because of it, I made what I believe was the only reasonable choice. Rather than going deep, I decided to go broad. And after that, if anybody interested, we can to deep any topic, certain topic. So now the core message of my presentation is actually shaped by trend I have observed in my own working experience. As I mean, the growing tendency to simplify and beautify transit planning by focusing on map visualization. So we can hear such terms like straight, bold, intuitive, and actually pleasing to the eye. And what today exactly, I will dare to explore a compromise between science and art in the practice of route network planning. So actually, I believe the most effective solution often emerge from a fusion of both data-driven analytic from one side and creative intuition from the second. But we say, but I want to underline that science without art is insufficient. But art without science, it's impossible, at least for any planners who cares about both quality and economic of transit service. So now two words. So now actually two words about my background. Originally, just to understand why I can speak about transit. So originally, I'm from Moscow, Russia. After Transportation University Work and Research Institute in Moscow. So you see, it was in previous century, actually, we work for horse transportation at that time. After that, I immigrated to Israel and actually worked there from a bus cleaner to manager of transit planning department in a Dun company. So you see, oh, big Dun now they have more than not just buses, but LRT, BRT, and other components of transit service. And after that, I come to Toronto, and now I'm working for WSP company. It's a multi-purposes consulting company. You see these parameters, more than 50% belong to transportation. And transportation, actually, you see this description of transportation department, let's say. So actually, you see, we touch all ingredients of transportation. Actually, I am working in transit and rail, and now maybe even more, I contribute my time in this field and field of electrical bus implementation. So we do feasibility study. We did. If we come, I will show you. So our experience from this point of view. And so actually, this is introduction. If no questions, I can go forward to the lecture, to the sorry, to the presentation. Okay, so actually, what I said, we try to explore any compromise between science and art in transit planning. So now actually a slide maybe speaks better than me. You can see that left side, this is a, let's say, science data-driven approach that actually we have any strong structure of processes that we come from macro to all this. We will speak about this too, and coming to the passenger at the end of all, after all this analytical uh, procedures and analyses. And from the other side, this is exactly what I found what I found today is any approach that actually based on these points, these principles, what you see here. I just focus it. And actually, this is I can say that it's not logical principles, not logical. So you see that actually we can say that each of them, it's okay. But a problem, two problems I see here. Problem number one, that if we use these principles, we should understand, we should know how to, we should know right determination of each of these points. What's duplication? What's directness? What's frequency, high frequency routes? For example, here for North America, 15 minutes high frequency route. For I don't know, Russia and Europe, 15 minutes, it's not very high frequency route. So we will speak today about these parameters, and I just want to show that it's not so obvious, and duplication might be effective and not effective. Route directness, it's not so obvious as well. So this is a problem number one here, that it's not very determined. And the main problem may be even that this is such kind of universal approach. They come with these points before analysis, not after. And it's a universal approach actually mostly to all city. They come exactly with these principles and say, let's apply them. So again, my understanding, you can speak about this, but after analysis and not before. And if we speak about analysis, so what I said in my previous slide, so all these principles, they sometimes you can see it's presented like any analytical results. Okay, we found low frequency routes. Let's write it's bad. We found any duplication that even maybe not determined what is this, but we found that in the map we see some routes overlapping each other. Okay, it's bad. So we see some curve routes. It's bad. So this is like result of analysis. And I think analysis should be done like in a platform of cost-benefit analysis. So actually based on these balances. So one balance between transit supply and economic, and other balance between transit supply and travel demand. So, and actually when you just you should analyze, calculate rational. I don't like word optimal, but rational balance between rational balances. And when you find them, actually, this is you prove your decision, your solution, and you can using this cost-benefit analysis to you can select preferable option. So, and sometimes it doesn't matter how many duplication or how many direct or indirect routes. So you calculate final results. So you need here, but to do this, you need to determine what is this level of service and how you analyze economic. So actually, from the other side, we have any maybe trend, so I would say super calculation. So, you know, now it's very popular transportation models. And now the generation number 6, I know, agent-based, active-based model, that it require a lot of efforts, money, budget, and very professional and complicated processes like validation, calibration. Actually, sometimes such model can take a lot of time and efforts, and after that you just don't have time to use this model for analytical for your transit planning. So not every city can afford such a process. And because of this, we need, I think, to find again any compromise between this precise calculation and any local experience. I will try to show this, how we can apply this, okay? So now this one more slide before we are going to the such exact things. Just any principles that I want to bring to the stage. So you see these 6 principles. Why 6? Because screen it's not so big. I can't put more. Just look. This is a number 1. What I want after that to prove this principle, transit, it's not just geography, it's travel demand on geography. This is exactly when we speak about route directness, duplication, even schedule. And second, you should analyze every route, but you can't make any decision by one route. You should analyze all network or cluster. It's like so sometimes one route maybe not doesn't have good performance, but if you remove this route, you bring damage to other routes. So, and because of this, actually approach of cluster, this is, I think this is right. So it's like in hockey team, you know, if you in defense, you don't bring goals for your team, but without you, they can't play. This is exactly the same principle. So you can see overall picture, not route by route. Now, better than the best. So you should consider not just the best option, not the fastest route, or no shortest path, or not the closed stop. You should again see all the picture. So you can find the best solution, but every solution that bring any results close to the best actually impact on, let's say, level of service. And so again, we should, to my opinion, use this approach as well. Now, this like oath of doctors, how it's called, Hippocrates. So you don't need to bring damage to existing passengers. Sometimes, especially when we use transportation model, we calculate travel demand, you know, distribution and generation, distribution, new passengers, but we don't take into account the passengers that we have today. And these passengers we can understand from ridership. So my opinion that we need to analyze what happens with existing riders when we are going to our genius transit planning solution. So sometimes maybe we can steal some new drivers from cars, but if we bring damage to our existing drivers, it will not be not a good solution, can bring to any negative results. So now one more. You should again use data-driven cost-benefit analysis, but we shouldn't ignore local knowledge. Not all quantified analytic can describe right picture. It more than this. If, for example, our quantified analytic doesn't not supported by any expert knowledge, it doesn't mean that expert is stupid, let's say. Sometimes maybe we did not right calculations. So we need to take into account expert knowledge and even sometimes to quantify it. I try to show this. And one more principle, this is we should our object of our analysis shouldn't be routes. Routes, this is a instrument and a tool for providing service to passengers, let's say. So our object should be area, so where is people living and working. So actually we need to analyze areas and not route. Route we can analyze, but just like to understand that this is a just tool for transit service, but our final decision should be done by analyzing areas. So because the areas, this is actually object of transit service. Okay, so actually, and last, such kind of, let's say, theoretical slide. This is a, you see, this is a processes that we should do providing transit service from macro planning. So macro planning exactly might be based on transportation models. It's a big to big investment project and so others. So actually it's responsible for concept, corridors, I know, rapid transit. So actually such kind of carcass of transit service our city. But after that, we come to the translation of this concept into the real network that based on not just on routes, even on route pattern, route alternative. So you can have here basic routes, short routes, long routes, express, diversion from the main trajectory, and for each of these routes we should provide frequency policy. So by day type and day period. So you should say, for example, you should say you have this structure of route alternative. Each route alternative for each day type, for each day period, should have headway, certain headway, certain vehicle type, and actually this is any result of this route networking. And after that, you go to the scheduling. So you translate this intervals headway to the real timetable, real block, vehicle blocks, and driver shifts. So at the end of all, you do, I don't put here roster, maybe and dispatching, and you go to the final customer rider. So, and what I want to say here, so all of these stages should be uh, uh, assessed from any this such kind of balance between level of service and cost. And important to say that every stage can destroy previous. If you, for example, scheduling, if you do not very effective scheduling, so what you plan in a previous stage might be just the passenger, let's say, just will not know that you provide any genius plan here because your scheduling actually destroy all your previous transit planning solutions. We will see it. Okay, so actually we come to the what I wanted to say. If can I go forward? Any questions? Maybe no. Okay, so I don't,
Yeah,
if
yeah,
I don't
go
see.
ahead. I think it's fine now. We can do the
Okay.
questions at the end of the session.
Okay, fine. So let's speak about what I said, determination of some parameters, and to understand if we determine them, after that we can analyze and assess them and to use it for transit planning. For example, let's start from such kind of meaning by name directness. It's most obvious meaning actually. So what I show this, imagine such situation. Two smart people discuss which route is more straight. One smart guy, this is a geometer, and second, this is a transit planner. So actually, this is a little bit tricky because hard to find a smart transit planner, but let's say we find it, okay? So, and they speak each other. And geometer say, look, what's understood, the route number one much more curve, look this. And I can, he said, I can prove it by any, let's say, geometrical analysis formulas. It's not big problem. And transit planners say, no, it's not fact, because actually we say that transit, it's not geometry or geography. This travel demand on geography. So what I mean? So look, say, for example, we have the situation when this very curved geometrically route, but you see this by these ginger arrows, this is like travel demand. If we, for each of a straight portion of this route, we have most travel demand going through this straight portion. So actually each passenger will go straight. What means straight? It's not much difference from if he does it by car, and so the plus minus the same trajectory he does it by bus. So actually, so most of passengers, they do straight movement for them. So some not so minor, they need to do all these curves, all these zigzags, but most of them actually provide direct right. In this case, for example, if most of the riders need to come from this origin to this destination, and so most of them need to do this one zigzag, and actually in this case, we can calculate that this route has passenger indirectness much more than this route. And so so actually what does it mean? For example, this a real example from any North American city. You see they built this route, so actually brown portion, this is a residential areas, let's say, and purple portion, this is any attraction. That might be commercial, retail, hospital, and others. So, and actually you see this route. So if you are living here and you want to go to this destination, you need to do all these curves. And actually, this is indirect for them. But if we had other distribution of demand, for example, a lot of here, a lot of here, a lot of here, this route is just combination of different routes, and actually it might provide good service for passengers, and it's no problem with this route, because just might be we don't have endpoints and others. So the same story about the same city. So we needed to prove that this route, it despite it looks by eye curve, we needed to prove that it's curve from passenger point of view. Okay, so now this is again, I stole this picture from one of book that actually support, I would say, art direction. What they say, this is a rational, this is a not rational, because they need to do detour. Again, I say the same. If we have this demand, it not rational, but if we have this distribution of demand, it might be rational. And other examples, the same. So this is a curve route, and this is how it looks demand. And so we can understand it's so what now I provide you any formulas how we calculate indirectness. So we distributed this indirectness in 4 such kind of parameters. So first of all, this is a geographical indirectness, and second, this is a passenger indirectness. So now indirectness might be calculated by distance or by time. Sometimes you do any curve by distance, but you go through, I know, dedicated lanes and certain highways that your time is short. And so now it's very so geographical indirectness. Actually, it's plus minus. It's very simple. So you take a ratio between route distance and distance between endpoints from time point of view, from distance point of view, and this is actually this ratio provide for you indirectness from the geographical point of view. You see this for this route, this indirectness by distance, this indirectness by time. But from passenger point of view, you like take all correspondence between all stops, and for each stops, let's say, correspondence matrix between stops of any route. And so actually you calculate for each correspondence how it's take by route and how it's take by direct way, let's say by car. And this ratio actually provide you information about, actually bring you to the indicator of passenger indirectness. And so when we calculate this, you see that passenger indirectness is good enough. So despite this route looks not very direct, so maybe they just don't have any endpoint here. This it's like two routes. So, and because of this, we don't cry that we need to redo these routes. This routes actually doesn't bring any problem for us when we calculated passenger indirectness. Okay, so now just again, so what in a from practical point of view, I have this system. If we have time, I can show its working system, but system works the next manner. So actually we have in any city, actually it was Almaty city, we use as well. So we have 240 routes. And for each routes, we calculated a lot of parameters, and each parameter we actually distribute by any levels. For example, geographical indirectness distribute by 6 levels. And so we can find routes with very significant geographical indirectness here. We found actually 2 routes that each route has 2 patterns, 2 directions. So actually we have 4 patterns with very huge level of indirectness. So you see these routes, even by eye you can understand it, but by eye it's easy to understand, but when you see all this system, it's hard to find. So we find these routes very fast, and now we say, okay, we have sub selection set from selection set. We have now for these patterns, and we find for each of these patterns passenger indirectness. So for 2 patterns of Route 68, passenger indirectness the same significant like geographical, but for Route 46 not so significant. And when we see structure of ridership, so you see this Route 46, blue dots, this is a boarding by stops. Green dots, this is alighting. So you see these people who board here, they will alight here, because who alight here, they can come just from here, just from this place. So actually we have significant correspondence parallel to this direct artery, let's say. After that, these people who board here, alight here, so they just direct enough as well. So actually you see 2 branches direct enough, and you see not a lot of people who do this loop to come from left side to right side. And because of this, after all, you understand again, this is a 2 just combined routes, and we have this passenger indirectness, but not so high like geographical. And this route opposite. So actually you see this a lot of boarding who come to the end point. Okay, these guys, they have direct movement, but these guys should do all this loop. So, and now I see so for example, from this picture, I understand that I need to bring these people to this endpoint by any other way don't do this loop. So actually we should this route exactly come to the pool of our problems that we need after that to solve them. Maybe we don't have a road network to come here, but this after that we will understand. But now, first of all, I put this route into the list of my problems that I need to check after that. Okay, so this is indirect. So now other story with route duplication. So again, if I ask some people what's route duplication, most of people say if you see on the map overlapping trajectories, this is a duplication. So now we do this any theory of duplication. So actually you see this table again, we distribute duplication by road duplication and duplication of connection of passengers. So road from the left side, you see road duplication. For example, okay, you see by your eye two red and blue routes, they overlap each other. But for example, this case, but stops of red and stop of blue in different places. So from bus volume, they duplicate. But from a passenger perspective, it's no duplication here, because actually each passenger should use certain stop for certain route, and actually they don't have duplication. In this case, they have the same stops, and our schedule built the way that we have bus bunching. So actually two buses work in this corridor, actually each near other. And this is a bad case of duplication. But if we distribute by schedule these buses, so we do any even interval between buses, maybe just one route help other, and we can't say that this is a bad duplication. This is a good duplication, because maybe in when they do some different trajectory, maybe so we come from two routes with not very frequent route, but they join into the frequent corridor. So we can't say that this is a bad duplication. This is an effective duplication. And we need differ between, let's say, this case, this case, this case. And this is just from a road duplication point of view. But the most important for us, this is a passenger duplication. So even if you don't have the same trajectory, but you have plus minus the same time, we can say that for these people, we have duplication. Despite buses, you don't see in the map buses go by the same trajectory. And actually, now, one more. So this is from geographical point of view, but you can't speak about duplication if you don't remind about service frequency. So just imagine you have this such kind of picture of duplication, and if route 3, for example, it's has one I know trip per hour, and route 2 has 10 trips per hour. Actually, hard to say that route 3 duplicate route 2, but route 2 duplicate route 3. And so actually, and after that, what I spoke about coordination. So actually, when you analyze duplication, it's not enough just to see by eye overlapping of routes. You need to understand road duplication, passenger duplication, take into account frequency, take into account schedule coordination, and to differ between effective and not effective duplication. And this is exactly what we do to understand issue of our plan, first of all. So this is some examples of effective duplication. For example, we have such a route that north portion is more heavy than south. So if we built our frequency based on this north portion, so number of buses calculated in north portion. So if we do this, and after that we have for sure the same frequency for all routes. And if we do this, we build frequency just on north portion. For example, we build this route that it takes 21 buses requirements. But if we do duplication, so we build one long route with low frequency and one additional route here with that to complete, let's say, this frequency to the required, so we can work with 90 buses. So actually we can just on this stupid case, we can save 2 buses. 2 buses, this is a huge saving because actually every bus annually require a lot of budget, let's say. So actually about this we will speak later. Okay, so I just want to say how we calculate passengers duplication by any example. Okay, so actually, let's say we have any route that you see this trajectory of this route, and blue point, this is a number of boarding. So this you see such kind of graph of ridership. So blue, this is a boarding, green, this is a lighting. And what you see, this graph, this is a load. This is an occupancy of bus, let's say. This is how many passengers within seat between stops. So it's like a load factor for ridership. So now just put here, mark here points where a lot of lighting. So here. So now we can understand that a lot of people actually come from here to here. But to know this as exact, we use correspondence matrix, inter-route correspondence matrix. So if you ask, so how I know this matrix, I will explain in a few minutes. But let's just imagine we have this correspondence matrix. So we have in this route, for example, 71 riders per trip. And these 71 riders distributed by this matrix. So from first stop, we have 28 boarding, and now in this row we see where they 28 guys going to what stop. So this is a decimal. This is, you can take, it's like any probability. So this is an, for example, very probable they come to this stop, and less. So actually, you see red by red color here numbers. This is actually a significant correspondence. Now, and about this coloring, I will tell in 1 minute. I will tell in 1 minute. Now, okay, so you have for this route correspondence for each of links between stops. Now, we our system calculate now for each of these links how many other patterns we have. And for example, other patterns, including our patterns. So what you see, this is a gray color, that this our pattern for provides service exclusive for this link. So nobody else, no one route more help to come from first stop, let's say, to this stop. So if we remove this route, actually no service between these stops. And between stop 1 and stop 2, we have 4 other patterns, and these 4 other patterns. So actually, you see this number of patterns by link. And this, for the same link, we calculate any parameters like waiting plus riding time. And after that, we calculate any duplication level. And in this coloring, you see duplication, you see like description of the duplication level. The more dark brown, the more duplication level between this pair of stops. And gray color show you that duplication level 1, it means that this route exclusive. And now we remember about this coloring and come here. So now we see distribution of our passengers by link with different level of duplication. And after that, taking this matrix, we actually calculate this duplication analysis of this route. So we see that for this route, we have total, for this route, we have 210 trips. What's 210 trips? This is all these links that we see here, that from stop 1 to stop 2, from stop 1 to stop 3. And from these 210 links, 113 links just exclusive, that nobody from this route serves them. From passengers' point of view, this is from 71 riders, 46 riders exclusive. And passenger kilometer, okay, I don't tell now, but doesn't matter. So now you see that actually this is a picture of duplication of this route. So we see that 65% of riders, they don't have any duplication, and very big duplication have just 6%, and intermediate duplication have 17%, 11% have, let's say, low duplication. And after that, taking into account this, we calculate duplication level from a trajectory point of view and from passenger point of view. And so we see that trajectory point of view, geographical point of view, duplication bigger than passengers, because we understand that we have a lot of passenger who is don't who they don't have any other solution except of their routes. And actually, we use the system that calculate for each route pattern this duplication level, and after that we find we find routes with high level of duplication, and again try to understand what we can, it's this duplication effective or not effective. If not effective, what we can do to solve this situation. This I just show you examples what I said. So this is our route we spoke now, and this is the two other routes, and you see any difference. So this route has what we said, this route in periphery of the city, and but has a lot of exclusive links and not a lot of high duplicated links. But for example, this route is well in a periphery, but almost we don't see exclusive links. So a lot of very duplicated, and so you see that duplication levels by passenger much bigger than this. And this any route within the city, but duplication level less than route this in periphery, despite by eye it looks very duplicated. And so actually this way help us to quantifiably to find any problematical routes. This again the same story what I said. We have this system that we have for each of pattern any calculation parameters. We find this direction by trajectory. We find most duplicated route by from a geographical point of view, and we find them and we start to analyze, and after analysis we understand what we can do. For example, this route 5A, this direction very duplicated and this direction not very duplicated. So it tell us that we, despite one of direction duplicated, we can't easily to remove this route or to do anything with. We need to think about this. For example, this exclusive portion of this route just for this. If we go north direction, if we remove this portion, so we have a lot of people going to transfer, if we even bring them to this portion. So now we need to understand, now we need to take this matrix, analyze, and to understand, maybe to shorten this route just to this point, not to bring it to the north point. And we divide this routes by 2, and maybe we can save one bus, and we create some transfer, new additional transfer, but it transfer not significant, and we need cost benefit to understand if new transfer guys, if we don't have a lot of new transfer guys, but we can save bus or any resources, we can understand if it's a good solution for us or bad. And so actually all this case we provide through this quantified analysis before we are going to do any conclusions. Okay, so now about, again, freedom of movement and system understanding. This now, I have to say, it's a little bit funny, because actually, first of all, majority of people use the transit in peak hours, so they are frequent passengers. They know they pass. They don't need to take into their head, their mind, all network. So they know they pass very well, and they don't need understand it's understood system or it's or not understood system. But even you build in Toronto, actually, let's say it's grid. We have routes north, south, east, west. Let's say it should be very simple. But anyway, if you see Toronto map, it's hard to understand. If you are living here, you don't know what happens here. So because this is any principle to do this, and the transit network should be understood. It's a little bit, I don't know, funny, let's say. And now we have, let's say, pocket guide. Actually, we don't need to keep in head all this network. You need to keep in our pocket just this equipment that can explain you how to go. So actually, I think this is a nice picture of route network. Doesn't say that this good route network. So it's better to go through all these points what I said. And transfer, what I want to say. This is again, now I see any trend that transfer become to be to come from a negative connotation to the positive. So if you say transfer grid, transfer network looks very sexy, let's say, because you have such very simple network that people can jump from route to route, and you don't have any curve route and other. So okay, I have no problem with transfer, but everything should be calculated. For example, this was picture in any book. I know this any unrealistic example. We have this 3 neighborhoods and 3 attractive areas: business, university, mall. And they say, now, if you create from every neighborhood to every attractive point. You have a lot of routes, a lot of, it's any messy structure, and you need a lot of not understood for passengers, and you need maybe a lot of resources. So it's better to do this. So every time passenger can come to this transfer point and do transfer, looks nice, and we can save resources. First of all, it's unrealistic. You never do this from everything to everything. No, you have actually link between neighborhoods, between this. And who said that this, if you need to take into account distances. So actually, this picture, I know, just very misleading. So if even again, if we remember our principle that transit, it's not geography, it's demand on geography. We need to understand demand. And when we understand demand, maybe we need just not three, just two routes. But to explain transfer without travel demand, this is a little bit strange. And so we need, what I want to say, we need to come to the cost-benefit analysis, it not just using such a principle like we saw in a previous slide. And we should take into account that every bus costs a lot of money in annual OPEX, and after that even CAPEX. And so to save every bus, this is a big challenge and results for each transit planning. So you need to do this work day by day to try to do your work, your system more effective, to find every bus is target for you to save it. So it's not to just to do such a big picture and to provide this transit system. So now one more schedule. Actually, it's hard sometimes. I don't see a lot of schedule analysis when they do transit planning. But schedule, what we say, schedule can kill all your transit planning. For example, look this example. This is a real example. This is from, oh, it doesn't matter, from any city. This is a you see this picture that show you very interesting situation, very interesting like analysis. So from by horizontal, you see departure of bus for certain trip, and by vertical you see run time. So for example, in 4 a.m. bus till one endpoint to other endpoint, it took him 80 minutes. And in 6 p.m., in 6 a.m., it took more than 100 minutes. So now when you see this picture, first of all, you can see headway interval between trips that not very even, but okay, so now we don't analyze it. But when you analyze runtime, you see very strange picture. So for example, this runtime bigger than this very small, this small, and this speak about the same, not other route, different route. This the same route, the same distance, the same stop. And you see such situation. So actually it's built just for, for paper schedule. In reality, after that it will be messy. Or other story is this. So you see, they give for each trip, they gave the same runtime. In the early morning, in the AM peak, midday, all times the same. Why? Because it's more easy schedule to do. But in reality, it can't work. So now the same picture about this city. So you see again the same runtime for without differentiation time by day periods. And this they have 8 routes, and you see 8 routes all time have, every route has the same speed, but big difference between speed between routes. So it's from 22 to 32. So actually for the same area. So actually when I see this, I understand that their plan doesn't work. And when we come to this result, you see this picture of real-time analysis. So you see for each trip, this every dot, every point represent different day. We have different some days for the same pattern for the each trip, and you see all times they have some minutes late than by schedule. And after that, all schedule come, to the messy. So, for example, this example, every such row represents schedule, and you see in the morning, real buses come around schedule, but in the AM peak, you can see any matching between schedule and how it works. So so what I want to say is that schedule kill all planning in route, all planning in a previous stage. And the same story about coordination between in corridor coordination. If you see this as the buses come together after the different interval, and because of this, instead of this, we built a schedule with an even interval for these two routes. So actually, we have this any systems that try to see, try to build even interval for corridor. You see this route, two routes come to the same corridor, and we built even interval for corridor. If again you don't build it, it's just not effective duplication. You build coordination. This is effective coordination. You should be supported by your ridership. For example, in this case, when you have within corridor correspondence, you need to build coordination. And then in this case, when a lot of people board in corridor, but after that alight in other portion of route, you don't need to build this coordination. So actually, all things should be analyzed, and you should make decision based on this analytics. So actually, you need do differentiation of headways by direction at the same period. So now most of the routes work the same headway, this direction and other direction, despite in most of the cases we have different demand. So when you build different directions, you can use after that any interlining skills and to build, so you can save this a lot of things. And the last about schedule. So when you use working rules, so sometimes because of you need to give meal or other, you actually reduce your service exactly within peak hours, and you calculate that you need to give, 5 minutes headway, but when you build your schedule, you provide in this case just 10 minutes. So actually, this is any difference between your intention and planning and after that scheduling. So actually, this is a all things that you should take into account if you want to do real transit planning and not just do any speculation around this. So, guys, do you have any questions maybe? Because I don't know.
Gera, can I have a quick question?
If you promise that it's quick, yeah.
And I have like 10 questions now, and I'm ask by the way, I'm missing something here, which is the you didn't talk about the hedonic factors in planning, like stuff like safety, or I'm sorry to say that it doesn't look good, it doesn't sound good, but it's real that some groups of people do not want to pass like through different different neighborhoods. Be like a safety issue, a political issue. And another thing, what about the crowding effect of people using the transit? Like,
You see this picture.
yeah, I know.
You just don't come yet, so to crowding, yeah.
Okay. Because I take it into consideration when I try to do modeling. I come from the modeling background. And the last one, which is future demand. Sometimes I really suffer with people that design transit when it comes to future demand. When we're trying to understand the picture in like 20, 30 years, not like the short-term 5-year period. Because you have to rely heavily on models. There's no other choice. But I really suffer with, like, you don't have like a real, and you know that models are rough, not exactly planning. You have to make a guesstimate about that. And I have a hard time, talking to people who design or who manage the operation of transit when we talk about. No, I'm gonna just.
No, so first of all, if I understand safety, so this look, what I showed now, I said we don't have time to speak about everything. What I say, I'm going broad, but anyway, it's maybe not very broad. I just touch some things that we come when we analyze existing service now. So existing planning, existing service. So we found, I just touch some parameters that I think that they are not, in a lot of analysis, they ignored them. So like duplication and I know directness. For sure, we need to analyze much more. I just touched to some of them. This is the one. The second, about crowding and ridership analysis, we have a very big theory how to analyze it. I don't know if we just can go through this today, maybe, but actually this is a big theory, a lot of parameters, and we built a matrix correspondence. So like you built the generation and distribution and model, we built this matrix correspondence based on boarding and lighting for each stop. And it's when this matrix much more exact than or distribution and generation and transportation modeling, because this is we have vector here. So let's say who alight in a second stop, we know that exactly it's come from the first. So we don't know this in transportation model because you have there from every area to every area. This we have any order. Because of this matrix much more precise, it's much more correct. And after that, using this matrix, we understand a lot of things about what I say. Don't bring damage to the existing. So I know that we need to think about how many additional potential passenger we will have. This is the other story. But this story, you need to analyze your existing system and existing passengers. For example, and you, after all, so we come this to the such situation when you provide any transit solution, and for existing passenger, for example, you have hourly 51,000 for any cluster passengers. And after you provide any solution, you say, okay, 70% of them even don't know about any your planning, but these guys have any benefit and these guys have any punishment. And so we know how it's it cost us 5 buses and this new resources. This is a cost benefit analysis. So you say, okay, I bring 5 buses and this it's causes this level of service picture for existing at least. And after that you come here and you do a lot of different transit solutions, and you do cost benefit analysis and you compare and you take and actually at least from the existing passengers. After that you take you calculate this and you need to understand how many potential passengers, because existing passengers we know, potential passengers we guess, let's say. We guess it by using any very complicated transportation modeling, but you know better than me that it's not always true, okay? So, but anyway, we can have any sensitive analysis how many potential riders we can have. But first of all, we need to understand what we provide for our lovely existing passengers, because if we bring damage for them, actually it can, like say, have negative reaction to all this system. And so going through all this ridership analysis, I don't know, so maybe I see times that I don't know if we can do today because everybody tight, I think so. But actually going through all this ridership analysis, and so just one example. For example, we have for each route, I say we calculate parameters. We find parameters passengers per vehicle hour. So actually this is a productivity. And we see that, okay, 2 routes, very huge passengers per vehicle hours. And I can say you that this is a subway. It's not very important for us. So, but this is a very high. We have 9 routes with very high productivity. Okay, we should be proud of these routes. But after that, we find other parameter, trip distance with low load from these 9 routes, okay? And we find this route 205. What this route say? You see that we find route with good productivity because a lot of passengers, but 40% of its trajectory, it's going almost without passengers, despite, if you see global picture, this is an excellent route because it provides per each kilometer, per each hour average good. So now we find this route. How we can solve this? How we can improve this? We cannot do again it just route by route. We need to understand a cluster. And we have any procedure that by duplication create cluster around this route. And we find 6 routes that very impactive of our route. And we find solution for all this cluster, not for all route, for just one route. So we analyze this route, 2 directions, and we understand that this route, what I say, a lot of people board in the beginning, now in the middle a lot of people alighting, and after that nobody. Because of this we see this load factor this way, okay? But opposite way, they start from this residential area. So anyway, we need to bring buses here. We can't cut it this. So we need bring, but here we have less passengers than there. And after that, we take all these routes around this and we do any analytics. And after that, we find any solution at the end of all here, that actually our solution, we do any calculation and we find any solution that we need to enhance any corridor route here. But for these routes, we need even to do any deadhead or express that come without passengers, but much faster to this end point to reduce loop time and to save buses. So actually, by this bus, maybe we need 18 buses to add to improve the situation. And after analysis, I can say that we just put not more than 8 buses. So actually 10 buses, this is a saving. And this is a huge, so your project don't take even 10% of a cost from your saving. So you spend this, 1 month of your work around this cluster, but after that you save huge amount of money if you save 10 buses. And this is what I want to say. This is my message. So we need to work not just like any compromise, evolution, revolution. So some planners say we need to do all network and don't do route by route or cluster by cluster. So tomorrow you wake up and you see new network. It doesn't work because you have some new malls, new subway station. All time you need to update your service, and you need to work according to clusters. We create cluster according to duplication theory. So clusters, this is a group of routes that impact in each other more than impact on other routes. So we create cluster, work in cluster. So now if we speak about so what I said, area. So our object, this is the area. We divide city into the cells, 100 meter by 100 meter. From other side, we have information, social demographic about each area. From other side, we have information how each cell serve by not just by closest stop, by all stops in any reasonable distance. So we take into account distance and frequency and how it's serves this area. And after that, we're going to this situation. So we calculate accessibility, walking accessibility level. The more green, the better, the more red, the worse. But again, maybe green for the empty area, we don't need, maybe red for the empty area, we don't need it. So we need to find any filter through population level and distance. So actually, and after that, you see this is a filter. So this is for any North American city. This is areas with not good walking accessibility level. And you see this as actually, so this is our target. Okay, so I just go very fast. So this is our target. So we find, so for example, any places where we have a problem with walking accessibility. And after that, we find a problem with connectivity between, so we say between this and this, we have problem with connectivity. So actually we have such, I don't know, we have working system that actually analyze this situation and find transit service gaps and efficiency gaps and crowding gaps, what you say. So I don't have time to explain everything, but what I say that we come very data-driven approach to analyze transit system and to analyze each proposed solution. This is about this. About 2 words about, and I will finish, I think. 2 words. So we have this electrification field that actually we built any system called BOLT, Battery Optimization Lifecycle Tool. And we work with this BOLT for feasibility studies for, you see, a lot of countries, continents. Even in Russia, we did one project a few years ago. And actually, this bolt built on a very strong database of transit system database and database of buses with their parameters. So we have library of electrical buses for different parameters. So what we do this actually, it's built, it works this way. So our bolt can calculate requirement of kilowatt hours for each trajectory between a pair of stops. So how it works? So we built all system. We take GTFS or as a source, and we built all network system. After that, we take all GIS from elevation, you know, topology, intersection, traffic, if we have, and we can work for different temperature, different road condition, air density, and we have library of electrical buses. So using all this information, we can calculate kilowatt hour for each portion of route. Okay, so actually, and this is our factors. So factors, this is a bus type, weight of bus, weight of passengers, and elevation, topology, and temperature, and all these factors we take into account when we calculate this portion of this route. After that, from this portion of this route, we see also pattern. So portion of route is between two vertical. And you see this route schematically. So in a horizontal, you see route stop by stop in scale of distance. By vertical, you see elevation. So now it's going up, after that going down. And this shadow, this is a number passengers. So we can by bolt calculate for each segment of this route required kilowatt hours by temperature, weather condition, number of passengers, bus type, and other, a lot of parameters. So, and after all, we say that if this route within this day type and day period going by this pattern, it require 1.3 kilowatt hour per kilometer. So now we analyze this is a one route. Now this is a bus block. So each this is a each gray rectangle, this is a trip. And now we see how it works when it's battery is gone. For example, we have safety level, and we can calculate that for this bus block, battery is gone here, despite this block was planned to this. So actually, these three trips cannot be operated. And actually, we did it for each bus block. This bus block complete, this bus block incomplete, and actually we can understand why. And so actually this we do after that using this bolt, we do this a lot of work. We do analyze charging strategy, night garage, mid garage, on route charging. We analyze scheduling, not just scheduling of buses, but scheduling of charging. So for in where we need to do charging. And all this based on this calculation of kilowatt hour per kilometer. And after that, we calculate energy requirements and taking into account about battery degradation, peak demand, and other. And after using this, we understand the requirements for infrastructure, charging cost, bus fleet, how many electrical buses you need to maybe to replace diesel buses, so and others. So and all this, actually, we have all this system that we do a lot of work. Will be interesting to work with this for other countries and companies, let's say. So all we have this capability. We work together with our Toronto York University, building this such kind of interactive tools for this electrical bus implementation. And actually, we do all this work with electrical buses. So actually, choice of e-bus battery types, bus battery types. What you see, I don't need to read it. And after that, we have all procedures to optimize charger location, optimize schedule of charging, find rational structure of vehicle block for certain bus electrical buses. So actually, I think just time is coming to the end. I didn't. Okay, so if you have questions, I can have answers maybe.
Hi. Okay, Eugenie.
Hi, Gera, can you hear me?
Yeah.
I just have short general question. Because I have been familiar with your ideas for a long time, and I absolutely agree that all ideas should not all ideas should be taken as true, and all ideas should be tested on data. I want to ask how often in your worldwide projects how often you encounter with partners, with customers who have stereotypes, have biases, like all routes should be straight, something like this. How often you face with this?
Okay. So you know the experienced presenter all start a question from the such kind of expression. It's good question. Okay, I say it's good question. Okay, so now I can say, for example, yesterday, I spoke with any client that they come to us for route optimization, and they bring us any paper, how they see it in the first page of paper. You can see all these parameters that I showed you. They say build for us hierarchical system, transfer oriented hierarchical system with low route duplication and with direct routes. This it was. They start from this is requirements for this system. So we need reduce duplication, we need do route directness, we need to go to the such kind hierarchy with transfer oriented. So what we need to do. I ask them why, because they say because it's better. This is was answer, and it's very frequent to what I see. So because it's these principles, they're like obvious, they easy to understand them, and it's nice looking in a map, because it's very popular to you maybe you know as well from your practice that people
Thank you.
and because actually all this presentation based on this, that I see it's a lot. Instead of to calculate, to analyze all this and to understand real problem, I don't speak even about schedules. They don't speak about schedule at all. But just to understand real problem, they want to go to this way just to do this beautification, let's say.
Okay, thank you.
Yeah, thank you. And Gera, one question. It was very interesting. These principles, how it can be reduced. You have an example of city that, imagine the structure from the logical perspective was structure, the bus network, and you start off this optimization process. you have an example like they can tell you how they can improve the transit time or an indicator of the level of service of the users. I mean, how much they can be improved. And in the case, this is from the side of the users, but from the side of the operators, the question is, it represents the biggest cost or not? Because often we will have this trade-off between the level of service of the users and the cost of the providers. It's supposed that when the level of service increase, I mean, when the level of service increase from the perspective of the providers is more expensive for the operator. What you have an example like with this kind of analysis, you are able to, how much you are able to improve in with one indicator, so one metrics you can indicate, and what represents this in terms of the additional or not, or maybe some additional cost for the operator.
Yeah, for example, the same Alma. So, okay, we have a lot of these examples. Let's say, now I have this here even Almaty working example of this. So, of this Almaty working example we did a few years ago, and we provide there 3 different scenarios, and with very significant saving of buses. So one scenario it was to save buses without change level of service, and the other scenario was to save buses but to bring it to increase level of service, and we have this. We provide. I think maybe Evgeny, he worked for this project as well. We provide this presentation to the municipality with this cost benefit, how they save and what happens with the level of service. And so they did, they select any preferable scenario. Now they try to start to implement, because implementation, this is a big trouble. But now maybe we 2 weeks ago we did presentation for one of North American cities. Requirement was without additional resources, the same buses, this plus minus the same resources, but increase level of service. So, and we redo all the network, but without any, let's do it duplicated, not duplicated. Exactly, we did this analysis, redo the service, and redo the transit planning service, and presented them, and actually now they, after the even public consultation, they actually take one of our scenarios that with the same resources we provide a service that we explain that service will be better, connectivity, walking accessibility, and reliability, because we provide new runtimes that can work, not runtimes that cannot work. But even increasing runtime, let's say decreasing speed, we don't bring additional resources. So actually we can say we don't save, but we save. Actually we save buses, because if we don't do this, we needed to bring additional buses, but we did any virtual saving. So actually all our project, we provide this cost benefit analysis information. So
yeah, no, okay, thanks. I don't know, it's someone else would like to do another question or comment. I think it is no more questions. So, okay, maybe we can stop here. So I don't know if it's possible, Gera, to have all this presentation and to share with the people that who attend.
yeah, it's possible, but yeah, but what I say, so a lot of things here. If anybody interested, it should go to too deep, let's say, because how to calculate, how to analyze, and at the end of all, I have this working. You know what I show you all this So actually, it's Almaty working how we, I know, do this. I know, for example, accessibility. You know, coming this, and you can do population above this, this below this, and you so all this working working system that you can see, and all this riders. So what I show you this table, if you see this, actually a lot of parameters calculated, and you can select and see and see routes for each of these so that actually satisfy these parameters and work with this. So actually all this is working, and all this is all wisdom that I told today, it's within this system, let's say. All duplication, directness, everything is here. Just I just wanted to explain, let's say, the meaning and the rationale of using this. But all this is sitting here, actually.
Okay.
I'm going to share we've recorded this webinar, and so we'll publish it on YouTube, and I'll distribute the link via LinkedIn so everyone can watch it.
Okay, so thanks a lot, Dr. Gera. We really appreciate your time and your presentation, and you share your knowledge about this. I think was very interesting about how to optimize all of this bus network, because really it's a huge topic, in fact, no, because it's challenging. We're having a lot of challenge. First, we need to provide a good quality of service of the public transport network. That means talking level of service. Yeah.
If anybody interested in more deep any certain topic, will be glad, you know, because I understand that within 1 hour, 1.5 hours, I just a little bit run faster than I wanted, but anyway, it's
okay.
So,
okay, no, was good. So okay, so thanks a lot. We really appreciate your time. So it's no more questions. So we can organize later something or on another seminar to go maybe deeper in one of the details if you want. So.
Okay, so do you want me to send this presentation? Yeah.
Yes, email it. Yeah, email it to me. That'd be great.
It's okay. We will find the solution because it's a big size, but okay, doesn't matter.
Thank you.
I will send you with a pigeon. Okay.
And thanks everyone else for joining.
Thanks.
Okay, thanks everyone.
Bye.